Hi everyone. Today I'll be presenting a very influential paper in natural language processing titled Efficient Estimation of Word Representation in Vector Space. This paper introduces what we call now word to vec, and it is fundamental change how machine represent and understand a language. And before this work, language was mostly treated as a discrete symbols, and after this work, we started thinking about a language as something that lives in a contiguous geometric space. By the end of this talk, I'll want you to understand not just what this model does, but why does it work and why something very simple ended up being so powerful. Let's start with a very brief basic question. How do we represent words in the first place and why do we need a better word representation? Traditionally in NLP, words were represented using something called one-hot vectors. If you look at the example on the slide, you can see that each word is represented as a vector, where only one position is 1 and everything else is 0. So for example, cat might be represented as 00100 and dog might be 00010. So mathematically this is convenient, but conceptually it is extremely limited because in this representation every vector is completely independent. There is no notion of similarity. And from the model's perspective, cat and dog are just as different as cat and something completely unrelated like airplane. This means the model cannot generalize. If it learns something about the dog, that knowledge does not transfer to cat at all. So effectively, the model has to learn everything from scratch for every single word. So what we actually want is a representation where meaning is encoded, where similar words are close to each other and related to words share structure. For example, we want cat and dog to be similar, and we want relationships like Paris to France and Rome to Italy to be reflected somehow in this representation. So the question becomes, how do we design a representation that captures meaning? That comes to the goal of the paper, that what the paper proposes. This is exactly what paper they strive to solve. The goal is to learn a mapping from each word to a dense vector in continuous space. Instead of huge sparse vector, we now have compact vectors, say 100 or 300 dimensions, where each dimension captures some latent aspect of meaning. And importantly, in this space, similar words end up closing together, and relationship between words become direction in the space. So for example, the direction from man to woman is no longer symbolic. Uh, This is a very powerful idea because it means meaning is no longer symbolic and it's geometric. But there's a challenge here. We are dealing with a massive data set, billions of words and very large vocabularies. So the model must only not be accurate, but it's also should be extremely efficient. So, and this is where the key philosophy of the paper comes in. We have to trade off between speed and accuracy and use simple models plus massive data. This turned out to be the winning strategy. Now, why this work is important? This leads to one of the most important insight of the paper. Words can be represented as points in a geometric space and where meaning and relationships naturally emerges. If you look at the diagram, you can see the vector from man to woman is very similar to the vector from king to queen. This often is called gender direction. And now this lead to famous analogy. King minus man would be equal to queen minus woman. This is called gender direction. This is not something we programmed explicitly. The model was never told about gender or royalty. It simply learned patterns from the data. So what this shows is the language has underlying structure, and when we learn representations correctly, the structures become visible. This idea is very powerful because it makes meaning computable and we can now do arithmetic with words. And this is why this paper had such a huge impact, and it laid the foundation for almost everything that came after in NLP, including the modern models like BERT and GPT. But all of this is built on a very simple principle. Let's discuss the distributional hypothesis. The principle is known as distributional hypothesis. The fundamental principle. You shall know a word by the company it keeps. What this means is that words that appear in similar contexts tend to have similar meanings. For example, if you look at the sentences like the dog is barking and the cat is mewing, you'll notice that dog and cat appears in very similar contexts. So even without knowing what these words mean, we can infer that they are similar. This is the key idea. The model never sees definitions, it never sees labels, it only sees patterns of co-occurrence. So we define something called context window. Context window. We take a word in sentence, the center word, and look at the word around it. Let's say we take mouse and look at the word around it. For example, in this sequence, the center word is WT, and the surrounding words from the context are WT minus 1, WT plus 1, T minus 1, T plus 2, and T minus 2. Now the learning is a problem become very simple. Either we predict the center word from its context, or the context word from the center word. And by doing this across millions or billions of sentences, the model starts to learn which words behave similarly. And that's the key insight of the entire paper. Now come to the context window. Now let's take the key idea we just discussed. The meaning comes from the context and make it more precise. To do this, we define something called context window. Imagine you are reading a sentence and at any given position you focus on one word. This is what we call the center word. And then you look at the words surrounding it. Might be two words to the left or two words to the right. These are called context words. Context words. Here, WT is the center word and everything around its context. This window size, how many words we look at, here we have two. This window size, how many words we look, is a design choice and is actually affect what the model learns. So, if the window is small, the model focuses on more like on grammar, things like verb, forms, and syntax. And if the window is large, it captures more semantic information like topics and relationships. So already we see something interesting. The definition of context directly shapes what kind of meaning the model learns. Let's take an example. The quick brown fox jumps over the lazy dog. If the center is fox and when the window size is 2, we have context words like quick and brown, jumps and over. The model learns meaning by predicting within this window. So similar context means similar embeddings. Now, window is the source of all learning signals. We turn this context into a prediction task. Let's look at the language modeling. What do we next is formulate this and as language modeling problem. So what is the language modeling? At this core, language modeling means predicting a word based on the other words, based on the given context. For example, if I say the cat sat on the, what should be the next word? You can immediately guess the missing word, maybe probably the mat. But what this means to you as a human is implicitly estimating a probability. What is the probability that the word given is its context? And that's exactly what we train the model to do. Model learns by maximizing the probability of the correct word given its context. Formally, we want to model learn something like this probability. The probability of a given word given its surrounding word and the context. But in this paper, instead of just predicting the next word like traditional languages, we use the context window in a more flexible way. We either predict the center word from the context or predict the context from the center word. And this is called the learning signal. Now, early neural models tried to do exactly this, but they ran into a major problem. Then comes the neural network language models, NNLM. Before word to vec, one of the main approaches was neural network language models, or NNLM. First, you take the context words, typically in one hot form, and map them into dense vectors, map them into dense embeddings. This is called the projection layer. So already we are learning embeddings here. Next, these embeddings are combined and passed through a hidden layer, which introduces non-linearity and allows the model to learn complex patterns. And finally, the model is the model outputs a probability distribution over all the possible words in the vocabulary. So for every input, the model is trying to assign a that uh, probability to maybe tens or hundreds of thousands of possible words. This is very powerful. It captures the complex uh, relationships and to learn embeddings at the same time. But there's a major problem. What is the problem? The problem is it's very complex and computationally costly. Let's look at the computational bottleneck. The most expensive part of the model is the final step, the softmax layer. And because every prediction, the model has to compute a score for every single word in the vocabulary. So if your vocabulary has 1 million words, that means 1 million computation for just one training example. And remember, we are training for billions of words. So this become completely impractical. On top of that, the hidden layer adds additional computation, making things even slower. So even though NNLM works well, it does not scale. And this is exactly where this paper makes a breakthrough.
Up to this point, we've seen how traditional neural language models work, and we've also seen where they struggle, mainly with computational cost. Now, this slide introduces the central breakthrough of the paper. The authors observe that the biggest issue is the hidden layer and the larger output layer. The computational grows with vocabulary size, and this makes it extremely hard to scale to real world datasets, especially when we are dealing with billions of words. So now the question arises, do we really need hidden layers to learn word meanings? And their answer is no. They propose something radical for that time. Remove the hidden layer, use simpler linear models, and learn by solving prediction tasks. So now the new approach is to simplify the structure and scale the data. This leads to the key philosophy of the paper. Word meaning can be learned efficiently without deep networks. And from this idea, they introduced two simple but powerful models, CBOW and skipgram. On this slide, we see the two core models proposed in the paper, which is the CBOW and the skipgram. So we'll understand these two models in the further slides. In CBOW, we take the surrounding words, the context, and use them to predict the center word. So information flows from multiple context words into one prediction. In skipgram, we reverse this idea. We take a single word, the center word, and use it to predict multiple surrounding words. So now let's understand CBOW, predicting a word from its context. So here we have a sentence like this dash is barking loudly. So here the context words are the, is, barking and loudly, and the model predicts the, is, barking loudly. These are our context words. The goal of CBOW is to use these words to predict the missing word, which is dog. So what does the model do? First, each word is converted into a word embeddings, and then all these vectors are combined typically by averaging. So first we create the word embeddings, then we average them out, and then the model predicts the dog. So now let's understand about the architecture and working of this model. The hidden representation is simply the average of context word vectors. So let's understand the step-by-step working. So first of all, we take the context words. So if we have C context words, we compute the sum of their embeddings divided by C. This gives us a single vector that represents the entire context. Then we use this vector to predict the probability of each word in the vocabulary. And this is done using a softmax function. So we have used softmax. Even though the model is simple, the cost still depends on the vocab size, which is why we later need optimizations. But notice how simple the model is. There is no hidden layers, just averaging and prediction. So now we move on to the second model proposed by the paper, which is skipgram. Now we flip the idea completely. Instead of predicting the center word, now we take the center word, for example dog, and try to predict the surrounding words. So suppose here we take word dog and then we try to predict the surrounding words, which is the is barking loudly. This means that for each word we create several training examples, and this is very important because it allows the model to learn much richer relationships. So the pipeline becomes take a center word, convert it into an embedding, predict multiple surrounding words, and then repeat for every context position. So here we can see the example as well. Suppose we take our input word dog, then we create a word embedding for that dog vector, and then this word embedding is converted into a shared representation, which helps us in predicting the final the is barking loudly context words. This makes the scriptgram especially powerful for learning semantic relationships. This is good for semantic relationships. Now let's understand the architecture and working of the skipgram model. So here you can also see the diagram. The process is, as I have earlier explained, take a center word, convert it into an embedding, then predict each surrounding word. But the key part is the training objective. So here, this is the training objective. The model tries to maximize the probability of all context words given the center word. So here you can see the formula where here T denotes the total number of words in corpus, C is the context window size, WT is the center word, and WT plus J is the surrounding or the context words. Then the model tries to maximize the probability of all context words given the center word. So for every word in the sentence, we look at its neighbors and try to make those predictions as accurate as possible. This means words that appear together frequently will have similar embeddings. So this is the probability model. Here we try to calculate the probability, and this is the full objective. Here we try to maximize this probability so as to predict the context words. So skipgram learns embeddings by maximizing similarity between words that appear together. Words that share context get pulled closer in vector space. This is the benefit of using skipgram. So skipgram is essentially learning by reinforcing co-occurrence patterns. Now let's talk about the bottleneck which is in this paper. So now that we understand how CBOW and skipgram work, we run into a very serious problem. When we try to train these models at scale, and that problem comes from the softmax function. As I've told you earlier, we use softmax and that is creating a problem now. So this issue is that the vocabulary size can be extremely large, anywhere from 1 lakh to over a million words. And for every training step, the model needs to compute a probability distribution over all these words. That means for every prediction, we compare the current word with every word in the vocabulary. So here you can see the summation. So this summation is where we calculate the sum of the every word in the vocabulary, and this is the main bottleneck as this is very large. So if the vocabulary size is V, the computation of this term alone becomes V, and this is extremely expensive. But there's the key insight, which is most of these computations are wasted. And this is what the authors of the paper noticed, that this is the where the most of the computations are being created. When predicting context words, only a few words are actually relevant, the correct ones. All the other words contribute almost nothing. So we are doing massive computation for almost no useful information. And this is what we call the softmax bottleneck. So the question arises, can we avoid computing over the entire vocabulary? And the paper proposes two brilliant solutions for this, which are the hierarchical softmax and the negative sampling. So now we'll try to understand these two. So yeah, so this is the hierarchical softmax method, which makes the training efficient. So instead of treating the vocabulary as a flat list, we organize it into a binary tree. Each word is placed at a leaf node of this tree. Now, to predict a word, we don't compare it with all words. Instead, we simply follow a path from the root to that word. So, we traverse from the root to leaf, making a sequence of binary decisions. At each step, the model makes a binary decision, go left or go right. This reduces the computational cost. So, predicting a word becomes a sequence of decisions. This reduces the complexity from O of V to O of log V. This is a huge improvement. For example, to predict the word dog, we might go root left left dog. This reduces the computation drastically, as we can see it. So instead of evaluating every word, we only evaluate a small number of decisions. But there's an even simpler and more practical method, which is the negative sampling. Now we come to one of the most important ideas in this paper, and this is very useful in real life as well. So this is negative sampling. This idea is extremely simple but very powerful. Instead of trying to distinguish a word from the entire vocabulary, we only compare it with a few selected words. For each training example, we create positive pairs and negative pairs. The positive pairs are the words that actually occur together, and the negative words are randomly sampled words that do not occur together. For example, dog barking. This comes into the positive pair, whereas dog table is a negative pair, dog car is also a negative pair. Now, instead of solving a huge multi-class problem, we convert it into something much similar. And you have already known that for binary classification, we can use sigmoid. So this now becomes a binary classification problem. So here the training objective becomes make real world pairs similar, make random word pairs dissimilar. So positive pairs vectors move closer, negative pairs vectors move apart. And this directly shapes the geometry of the embedding space. So this is the mathematical objective function as proposed in the paper. So here you can see the first paper is the positive sample, and the second term is the k negative samples which we have taken so as to model it as an binary classification problem. Here k is the number of negative words, example 5 to 20. Now here also the complexity is O of k, but here the k is much smaller to the vocabulary size v, as here the k is the number of negative samples we have chosen. And this is what makes Word2Vec extremely fast and scalable.
So now that we have seen the models and the training tricks, let's step back and ask a deeper question. Why does the word to vec work? At a high level, when the model is doing very simple, it's repeatedly adjusting word vectors based on how words co-occur in text. And every time two words appear together, their vectors are nulls closer. And every time they don't appear together, especially in negative sampling, their vectors are pushed apart. And over million or billions of such updates, a structure starts to emerge. And words that appear in similar contexts end up close together. And more interestingly, relationships between words become consistent in directional space. So what we get is not just similarity, we get structured geometric space of meanings. And this is the core reason of word to vec works. That language has statistical structure and the model converts that into a geometry. So word meaning emerges from this geometry. Now that we have understood the why the model works, we need a way to evaluate it, and let's evaluate the word embeddings. And this paper proposes a very clever method, analogy tasks. This task looks very similar to kind of if A is to B, then what is C is to. So these type of analogy is this paper proposes. Like if king is to man, then what a queen is to? What should be the answer? The ideal answer should be woman, right? So, but what's interesting is how the model solves this. It computes vector king minus the vector man and plus the vector woman plus the vector woman, vector b plus vector a plus minus vector a plus vector c, and then finally it finds the vector whose vector is closest to the result. So if the embeddings are good, the answer would be queen. This test is not just checking similarity, it's checking whether the model has learned relationship between words or not. And that's a much deeper level of understanding. Many more examples include like if Paris is to France, then Rome is should be like Italy, and big bigger than small smaller. Now let's compare different models and the result section. Now we'll compare to the traditional models like NNLM or RNNLM and the new models like this paper project SIBO and the skipgram. The results are quite surprising. The skipgram model performed best on semantics. So the skipgram performs best on the semantics, things like countries, capitals, and analogies. While SIBO model performs best on syntactic tasks such as grammar and word forms. But the most important takeaway is that both SIBO and skipgram outperform the more complex neural models like RNNLM and NNLM. So they do this while being much faster even. So again, we see the central theme of the paper. Simpler models plus large data is greater than complex models. Now let's look at the real life examples and the applications of these models discussed in this paper. On the left side, you can see the actual word embeddings. Like these are just vectors of number representing word like cat, kitten, dog, and houses. These are the real vector embeddings. So individually these numbers don't mean much to us, but what matter is how this vector relates to each other. And when we reduce this high dimensional vector into a 2D vector, uh, something very interesting happens. We see that cat and kitten are closer together and dog is also nearby, but the is very like far to this, and this form a cluster of similar concepts. And similarly in the lower diagram, man, woman, king, queen form a structured pattern. Like the relationship from man to woman is like similar relationship to king to queen, and also the relationship from man to king is similar to woman to queen. So this is exactly the idea we have discussed. Relationships become directions in vector space. So now let's see why this is useful to the real worlds. These embeddings are used in a like what are the applications of these embeddings, and for example in search engines to understand meaning, not just keywords. Also chatbots to interpret user queries, and sentiment analysis to understand opinions, machine translation to map meaning across languages, recommendation systems to find similar items. And in all these cases the key idea is the same: word with similar meaning have similar representation.
So now let's move on to the code demo. So here we are implementing the two word-to-vec models, the skipgram and the cbow. So here we are importing the libraries and then we are creating the dataset from the IIT Jodhpur websites and IIT Jodhpur important resources. So these are the links from where we are scraping the data for IIT Jodhpur. After scraping, we are reading the PDFs and then we are the cleaning the corpus and creating a cleaned corpus after removing all the stop words, etc. And then finally plotting the cloud words. So here you can see the total number of documents are 126 and the tokens are these many, and this is the word cloud. So here IIT Jodhpur emerges as the top word, the institute technology, these are all the words in the data set. Now we move on to the model training. So here we are defining the hyperparameters where we have chosen the embedding size as 300 and the window size, the context window, which we talked about in the presentation, as 5. The number of negative samples, which is k as shown in the presentation, is also 10 here. And the epochs chosen for CBOW are 70 and skipgram is 60. These are hyperparameters, so we have decided by training on multiple hyperparameters. Then we move on to the vocabulary creation. Here we are creating all the vocabularies by tokenizing the corpus and creating the vocabulary for it. Next, we are converting those texts to indices. Here we are converting those texts. Here we are creating the negative sampling. So you can see here we are doing this creates the probability distribution for the negative sampling. We raise frequencies to the power of 0.75. This is a key trick from the original word-to-vec paper to balance frequent and rare words. Next is the data preparation. These are the helper functions which we are using, the sigmoid, the sample negative, and this is the data preparation we are doing for CBOW and escapegram respectively. Then we initialize the embeddings. Here we are using the Xavier style initialization to initialize our embeddings from when they for the first epoch. And this is the major training loop for the CBOW model. So here we first initialize the context vectors, and then we take embeddings of context vectors and compute their average. This represents the entire context. After this, we compute similarity between context vector and correct target word. We sample incorrect words to train the model what not to predict. And here this is the loss function. As you can see, we maximize probability of correct word and minimize probability of incorrect words. After this, we do the back propagation. These gradients measure how wrong the predictions are. So here this is the back propagation. After this, we do the weight updates using gradient descent to improve predictions as we know how to train a neural network. After this, we print the epoch and the loss, and this is the skipgram training loop. Here we also first take one word embeddings as input, then we predict one context word at a time. Similarly, we do the negative sampling here as well. So this is the negative sampling which we did. Uh, Here only one word embedding is updated at a time, unlike CBOW, as we've discussed in the presentation as well. After this, skipgram learns by expanding one word to predict multiple context words. So we train both models separately and then we evaluate their performance. So here you can see the hyperparameters as the dimension is 300, the context window size is 5, and the negative samples are 10. So this is you can see the loss is decreasing as we move on with the epochs, and the final loss is around zero point 0.4, and for the skipgram it is around 2. So this is the final embedding shape of 300 dimensions for 7290 tokens. So here we can see that we printed the final word embedding for the word student. So this is the CBOW embedding of 300 dimension. After this, we use the semantic analysis, as we discussed in the presentation as well. We try to find out the analogy. This is the code for analogy. So, for the word research, the CBOW is predicting capture, sensitivity, etc. Although these are not that relevant for the real world, but this notebook is to see the performance of these models. So here you can see the scriptgram is performing much better than CBOW, as the research is giving us department, area, project, collaboration, etc. After this is the analogy predictions. Like for the BTech, if it is undergraduate, then for MTech it is postgraduate. This is a very good analogy which the skipgram has predicted, and here you we can see how this model is able to learn the semantic meaning of the language. Then we reduced the dimensions to 2D for better visualization. Here we applied PCA to do the same. So here you can see these words like the MTech department, research, PhD, etc. all are coming very close, which means the model is able to learn the semantic or capture the semantic meaning of the corpus. So this is similarly the scriptgram PCA projection, and here also BTech department, student, all these words are coming very closely, depicting how well the model is performing on such a huge corpus. And also here you can see that training is also done very fast.